Right now, as you read these words, there is a non-zero probability that you did not exist 5 seconds ago. Not in the sense that you were born 5 seconds ago, but that you, your entire consciousness, every memory you have of childhood, every emotion you've ever felt, every person you've ever loved, spontaneously assembled itself from random quantum fluctuations in the void. Your memories of breakfast this morning? Never happened. Your first kiss? A false implant. The entire history of human civilization you believe you're part of? A cosmic accident that exists only in your newly formed brain, floating alone in an infinite universe. This isn't science fiction. This is a serious prediction that emerges from our best understanding of thermodynamics and cosmology. And the truly disturbing part? The mathematics suggests it's statistically more likely that you're one of these spontaneous consciousness bubbles than a real person with a real past. The physicist Ludwig Boltzmann never intended to create an existential nightmare when he developed his theories about entropy in the late 19th century. Working in Vienna, struggling with depression, trying to understand why time seems to flow in only one direction, he stumbled upon an idea so strange that it would haunt physics for over a century. Boltzmann realized that the second law of thermodynamics, the principle that disorder always increases, isn't actually a law at all. It's a statistical tendency. Given enough time, truly infinite time, random thermal fluctuations could spontaneously decrease entropy. A broken glass could reassemble itself, a dead star could reignite, and most disturbingly, a conscious brain, complete with false memories of an entire lifetime, could pop into existence from nothing, persist for a moment, then dissolve back into chaos. Boltzmann himself recognized the paradox. If the universe is infinitely old and will exist infinitely into the future, then every possible configuration of matter, no matter how improbable, will eventually occur. Not just once, but infinitely many times. This includes configurations that look exactly like you, sitting exactly where you are, reading exactly these words, with exactly the memories you have right now. But here's where the mathematics becomes cruel. It takes far less of a random fluctuation to create a single conscious brain with false memories than it does to create an entire universe with a real history leading up to that brain. A Boltzmann brain requires only a tiny, localized decrease in entropy. An actual evolved human being requires billions of years of cosmic history, stellar formation, planetary evolution, the emergence of life, and the entire chain of causation that led to your existence. Think about what this means. Imagine you're trying to explain your existence. Option 1. The universe began 13.8 billion years ago in a Big Bang, expanded and cooled, formed galaxies and stars, created the elements necessary for life, produced a planet in the habitable zone of a stable star, generated self-replicating molecules, evolved those molecules through billions of years of natural selection into complex organisms, developed nervous systems and brains, created human civilization, led to your parents' meeting, and finally resulted in you, sitting here, conscious and reading. Option 2. Random quantum fluctuations in an eternal void spontaneously created your brain, complete with all your memories, 5 seconds ago. Which requires less of a statistical miracle? The answer is horrifying. Option 2 is vastly, incomprehensibly more probable. For every real human being that emerges through the long, arduous process of cosmic and biological evolution, an infinite number of Boltzmann brains should pop into existence, each one convinced it has a real past, each one wrong. If you accept the premises, an eternal universe, random fluctuations, the laws of thermodynamics, then you should conclude that you are almost certainly a Boltzmann brain. Your memories are false. Your reality is an illusion. You will dissolve back into the void in moments, never having truly existed at all. The physicist Sean Carroll calls this the Boltzmann brain problem, and it represents one of the deepest crises in modern cosmology. It's not just a philosophical curiosity, it's a reductio ad absurdum, a proof by contradiction that something in our understanding of the universe must be wrong. Because if our theories predict that we're almost certainly disembodied brains with false memories, and we have good reason to believe we're not, then our theories are broken. The question is, which part is broken? Is it our understanding of thermodynamics, our models of cosmology, our assumptions about the nature of time? Or is the universe actually telling us something even stranger? That the distinction between real and spontaneously generated consciousness might not be as clear as we think. To understand how physics arrived at this existential precipice, we need to go back to the fundamental question that started it all. Why does time have a direction? You've never seen a broken cup spontaneously reassemble itself. You've never seen smoke flow back into a candle. You've never seen a corpse come back to life. Time, in our experience, flows inexorably from past to future, from order to disorder, from low entropy to high entropy. But the fundamental laws of physics, Newton's laws, Maxwell's equations, even Einstein's general relativity, are time-symmetric. They work equally well forwards and backwards. If you filmed a planet orbiting a star and played the video in reverse, the physics would still be valid. So why does the universe have an arrow of time? Boltzmann's answer was statistical. Imagine a box containing a gas. Initially, all the molecules are in one corner, a low-entropy, highly ordered state. Release them, and they'll spread out to fill the entire box, a high-entropy, disordered state. This isn't because there's a law forcing them to spread out. It's because there are vastly more ways for the molecules to be spread out than to be concentrated in one corner. The system evolves toward higher entropy simply because high-entropy states are more probable. The second law of thermodynamics isn't a fundamental law. It's a statistical statement about probability. But Boltzmann realized this logic cuts both ways. If you wait long enough, truly infinitely long, those randomly moving molecules will eventually, by pure chance, find themselves all back in one corner again. The probability is infinitesimally small, but over infinite time, it becomes a certainty. This is called a Boltzmann fluctuation, a spontaneous, temporary decrease in entropy. And if small fluctuations can happen, so can large ones. Given infinite time, a fluctuation could create a solar system, a galaxy, a universe, or, requiring far less of a statistical miracle, a single conscious brain. Here's where the mathematics becomes precise and terrifying. Let's say you want to explain your current conscious experience. You could invoke the entire history of the universe, 13.8 billion years of cosmic evolution. But that's an enormous entropy decrease, an incredibly improbable fluctuation if we're thinking in terms of random chance. Alternatively, you could invoke a much smaller fluctuation, just enough to create your brain, right now, with false memories of the past. This requires vastly less of a decrease in entropy. It's still incredibly improbable, but it's far more probable than creating an entire universe with a real history. The ratio isn't even close. For every real observer that emerges through actual cosmic history, there should be an incomprehensibly larger number of Boltzmann brains that pop into existence with false memories. The physicist Don Page calculated that in certain cosmological models, the ratio of Boltzmann brains to real observers approaches infinity. Not just a large number, infinity. If you're trying to explain your conscious experience using only probability theory, you should conclude with near certainty that you're a Boltzmann brain. Your memories of childhood are false. Your sense of having existed for years or decades is an illusion. You spontaneously assembled from quantum foam moments ago, and you'll dissolve back into it moments from now. Now, you might be thinking, quote 3. But here's the problem. A Boltzmann brain would think exactly the same thing. If a random fluctuation can create a brain with false memories, it can also create false photographs, false other people, false physical evidence. In fact, it's still more probable for a fluctuation to create a brain plus a small amount of supporting evidence than to create an entire real universe. You cannot use your memories or your observations to prove you're not a Boltzmann brain, because a Boltzmann brain would have exactly the same memories and observations. This is where the problem transcends physics and becomes a crisis of epistemology, the study of knowledge itself. If our best theories predict that we're almost certainly Boltzmann brains, and if being a Boltzmann brain means all our observations and memories are unreliable, then we have no basis for trusting the theories that led to this conclusion in the first place. It's a self-defeating prediction. The cosmologist Andreas Albrecht put it bluntly. The Boltzmann brain problem is not just a problem for cosmology, it's a problem for the entire scientific method. If our theories predict that our observations are probably illusions, then we can't use observations to test theories. The scientific community has proposed several ways out of this nightmare. One approach is to reject the premise of an eternal universe. If the universe has a finite past and a finite future, then there isn't infinite time for Boltzmann brains to form. The Big Bang gives us a low entropy starting point, and perhaps the universe will end in a big crunch or a heat death before Boltzmann brains become probable. This solution is appealing, but it requires us to explain why the universe started in such a low entropy state in the first place, a question that remains deeply mysterious. Another approach involves the anthropic principle and the multiverse. Perhaps there are infinitely many universes with different properties. In most of them, Boltzmann brains vastly outnumber real observers. But we necessarily find ourselves in one of the rare universes where real observers can exist, because Boltzmann brains don't have the stability or longevity to develop science and ask these questions. This solution feels like cheating to many physicists. It explains our observations by saying we're lucky to be in a special universe, but it may be the best answer we have. A third approach is more radical. Perhaps our understanding of probability in infinite systems is fundamentally flawed. The mathematician David Albert has argued that we can't simply count configurations and calculate probabilities when dealing with infinite sets. Infinity breaks our intuitions about likelihood. Maybe there's a deeper principle, not yet discovered, that explains why real observers exist despite being statistically improbable. This would require new physics, a revolution in our understanding of thermodynamics or quantum mechanics, or both. But there's a fourth possibility, one that's rarely discussed because it's so unsettling. Maybe the Boltzmann brain scenario is actually correct, and we need to accept its implications. Maybe you are a spontaneous fluctuation, and so am I. And so is everyone you've ever met. Maybe the universe is exactly as strange as the mathematics suggests. Maybe reality is far more fragile and temporary than we ever imagined. Maybe the distinction between, quote, 5 memories and, quote, 6 memories is meaningless, because all memories are just patterns of information, and it doesn't matter whether those patterns arose through evolution or through random fluctuation. This last possibility touches on deep questions in the philosophy of mind. What makes a memory real? What makes an experience genuine? If a Boltzmann brain has the subjective experience of remembering childhood, of feeling love, of contemplating its own existence, is that experience any less valid than the experience of a real person? The philosopher Derek Parfit argued that personal identity is not about continuity of physical substance, but about psychological continuity, the chain of memories and experiences that connect your present self to your past self. But if that chain can be created instantaneously by a random fluctuation, what does that say about the nature of identity itself? Consider this thought experiment. Imagine two people, identical in every way. Same memories, same personality, same conscious experience. One of them has a real past. They were born, they grew up, they lived a life that led to this moment. The other is a Boltzmann brain. They popped into existence 5 seconds ago with false memories of that same past. From the inside, from the subjective perspective of consciousness, these two people are indistinguishable. They have the same thoughts, the same feelings, the same sense of self. So, in what sense is one real and the other false? Is there a meaningful difference, or is the distinction just a matter of external history that has no bearing on the actual experience of being conscious? This question becomes even more complex when we consider the nature of time itself. In Einstein's theory of relativity, The past, present, and future all exist simultaneously in a four-dimensional space-time. The flow of time is an illusion created by our consciousness moving through this static structure. If that's true, then the distinction between a real past and a false past becomes even murkier. A Boltzmann brain's false memories are just as much a part of the structure of space-time as a real person's genuine history. They're both just patterns of information encoded in the physical state of a brain at a particular moment in time. The physicist Carlo Rovelli has suggested that time itself might be an emergent property, something that arises from our limited perspective rather than a fundamental feature of reality. At the deepest level, at the scale of quantum gravity, there might be no such thing as time at all, just a timeless quantum state from which our experience of temporal flow emerges. If that's correct, then the entire concept of a past that leads to the present might be a cognitive illusion. Your memories don't point to a real history. They're just part of the current state of your brain, and the story they tell about the past is a narrative your consciousness constructs to make sense of that state. This brings us to a profound realization. The Boltzmann brain problem isn't really about brains popping into existence from nothing. It's about the nature of evidence, the reliability of memory, and the foundations of knowledge itself. Every time you remember something, you're not accessing the past directly. You're accessing a memory trace in your brain, a physical pattern that could, in principle, have been created by any process, including random fluctuation. You trust that your memories correspond to real events because that's the most plausible explanation in a universe with a low-entropy past. But if the universe doesn't have a low-entropy past, if it's eternal and fluctuating, then that trust is misplaced. The philosopher Bertrand Russell once posed a similar thought experiment. Imagine the universe was created 5 minutes ago, complete with all our memories, all historical records, all physical evidence of the past. How would we know? What test could we perform to prove that the universe is actually billions of years old rather than 5 minutes old? Russell's point was that we can't prove it. We simply assume it because it's the most reasonable explanation. But the Boltzmann brain problem shows that most reasonable and most probable might not be the same thing. The most probable explanation, given certain assumptions about cosmology, is that you're a spontaneous fluctuation. The most reasonable explanation, given our experience and the success of science, is that you're not. These two conclusions are in direct conflict. This conflict reveals a deep tension in how we think about probability and explanation. In everyday life, we use probability to predict the future and explain the past. We say, it's improbable that a coin will land heads 10 times in a row, so if it does, we suspect the coin is rigged. We say it's improbable that life arose by chance, so we invoke natural selection as a mechanism. But these probabilistic arguments assume we're sampling from a well-defined population with known properties. When we're talking about the entire universe, about infinite time and infinite possibilities, our intuitions about probability break down. We're no longer sampling from a population, we're trying to explain why we exist at all, and the usual rules don't apply. The mathematics of entropy is deceptively simple, but its implications are staggering. When Boltzmann formulated his equation, S equals k times the natural logarithm of omega, where S is entropy, k is Boltzmann's constant, and omega is the number of possible microstates, he gave us a precise way to measure disorder. But he also gave us a way to calculate probabilities in thermodynamic systems. And those calculations lead directly to the Boltzmann brain nightmare. To understand why you're statistically more likely to be a spontaneous fluctuation than a real person, we need to dive deep into what entropy actually means and why the universe's low entropy beginning is so cosmologically suspicious. Imagine a deck of cards. There's exactly one way to arrange the deck in perfect order: ace through king of spades, then hearts, then diamonds, then clubs. But there are more than 8 times 10 to the 67th power ways to arrange the deck randomly. If you shuffle the deck, you're overwhelmingly likely to get a disordered arrangement simply because there are so many more disordered states than ordered ones. This is entropy in action. Not a force pushing toward disorder, but a statistical inevitability arising from the sheer number of possible configurations. The universe works the same way. There are vastly more ways for matter and energy to be spread out randomly than to be concentrated in ordered structures like stars, planets, and living beings. Now scale this up to the entire observable universe. Our universe contains approximately 10 to the 80 atoms, each one capable of being in different positions, different energy states, different configurations. The number of possible arrangements of all these atoms is incomprehensibly vast, something like 10 to the power of 10 to the 120. Most of these arrangements are high entropy. Matter and energy spread uniformly. No structure, no complexity, no life. A tiny, infinitesimally small fraction of these arrangements are low entropy. Galaxies, stars, planets, organisms, brains. If you were to randomly select a configuration from all possible configurations, you would almost certainly get a high entropy, disordered state. You would not get a universe that looks like ours. But here's the critical point. Our universe is not in a high entropy state. Not even close. Yes, entropy is increasing. Stars are burning out, galaxies are spreading apart, the universe is becoming more disordered over time. But compared to the maximum possible entropy, we're still in an incredibly low entropy state. The cosmic microwave background radiation is almost perfectly uniform, with temperature variations of only 1 part in 100,000. The distribution of matter in the early universe was remarkably smooth. This low entropy beginning is what allows complexity to exist. It's what allows stars to form, planets to coalesce, life to emerge, and conscious beings to contemplate their own existence. The question that haunts cosmology is, why? Why did the universe start in such an improbable, low entropy state? If we're thinking in terms of random fluctuations, a low entropy beginning is vastly less probable than a high entropy beginning. It's like shuffling a deck of cards and getting them in perfect order on the first try. Not impossible, but so unlikely that if it happened, you'd suspect something other than chance was at work. The physicist Roger Penrose calculated that the probability of our universe's low entropy initial state, arising by chance, is approximately 1 in 10 to the power of 10 to the 123. That's not just a small number. That's a number so small it defies comprehension. There are only about 10 to the 80 atoms in the observable universe. Penrose's number has more zeros than there are atoms to write them on. This is where the Boltzmann brain problem becomes acute. If we assume the universe is eternal and subject to random thermal fluctuations, then over infinite time, every possible configuration will occur. But they won't occur with equal frequency. They'll occur in proportion to their probability, which is determined by their entropy. High entropy configurations are vastly more common than low entropy configurations. So if we're trying to explain our current observations, the fact that we exist, that we're conscious, that we perceive an ordered universe, we should invoke the minimum necessary fluctuation, not the maximum. We shouldn't invoke a 13.8 billion year history of cosmic evolution starting from an incredibly improbable low entropy state. We should invoke a tiny, localized fluctuation that creates just our brain, just our consciousness, just our false memories. Let's make this concrete with numbers. Suppose you want to explain your current mental state, your memories, your thoughts, your sensory experiences. Option 1. The entire observable universe, with its 10 to the 80 atoms, all arranged in the specific low-entropy configuration that leads to your existence. The probability of this configuration arising from a random fluctuation is roughly 1 in 10 to the power of 10 to the 123. Option 2. Just your brain, with its approximately 10 to the 26 atoms, arranged in a configuration that produces your current conscious experience. The probability of this configuration is still incredibly small, maybe 1 in 10 to the power of 10 to the 26, but it's incomparably larger than option 1. The ratio between these probabilities is so extreme that for every real universe that produces a real observer, there should be 10 to the power of 10 to the 97 Boltzmann brains that pop into existence with false memories. These numbers are so large they lose meaning. Let me put it another way. Imagine you're playing a lottery where the odds of winning are 1 in 10 to the power of 10 to the 123. You play once. You win. Would you conclude that you got lucky? Or would you conclude that the lottery was rigged? The rational conclusion is that something other than chance is at work. Either the lottery isn't random, or you're not actually playing the lottery you think you're playing, or your perception of having won is itself an illusion. The same logic applies to the universe. If our existence requires a fluctuation so improbable that it should never happen even over infinite time, then either the universe isn't random, or it's not eternal, or our perception of existing in a low-entropy universe is false. This is why cosmologists take the Boltzmann brain problem so seriously. It's not just a philosophical puzzle, it's a direct challenge to our cosmological models. Any model that predicts an eternal universe with random fluctuations will inevitably predict that Boltzmann brains vastly outnumber real observers. And if Boltzmann brains outnumber real observers, then you should conclude that you're probably a Boltzmann brain, which means your observations are unreliable, which means you have no reason to trust the cosmological model that led to this conclusion. The theory eats itself. The physicist Sean Carroll has spent years wrestling with this problem, and he's proposed a solution that requires rethinking the nature of the early universe. Carroll argues that the low-entropy beginning of our universe isn't a random fluctuation at all. It's a boundary condition, a fundamental feature of how the universe began, not something that needs a probabilistic explanation. In this view, the Big Bang wasn't a fluctuation from a pre-existing high-entropy state. It was the beginning of time itself. And the low entropy at that beginning is simply a brute fact about our universe, like the speed of light or the charge of an electron. We don't ask why the speed of light has the value it does, we just measure it and build our theories around it. Similarly, we shouldn't ask why the universe started with low entropy. We should just accept it as an initial condition and move forward. This solution is elegant, but it raises new questions. If the low entropy beginning is a boundary condition, what determines that boundary condition? Is there a deeper theory that explains why the universe must start with low entropy? Or is it just an arbitrary choice, one of many possible initial conditions, and we happen to live in a universe with this particular choice? The physicist Lee Smolin has suggested that the initial conditions of our universe might be the result of a previous universe collapsing and rebounding. A cosmological natural selection where universes that produce black holes spawn new universes with similar properties. In this scenario, low-entropy beginnings are favored because they lead to universes that produce more black holes, which produce more offspring universes. But even if we accept that our universe has a low-entropy beginning as a boundary condition, the Boltzmann brain problem doesn't entirely go away. It just shifts to the future. If the universe continues to expand forever, eventually reaching a state of maximum entropy, a heat death where all matter and energy are spread uniformly and no structure remains, then we're back to an eternal, high-entropy state where random fluctuations can occur. And over infinite future time, those fluctuations will produce Boltzmann brains. Lots of them. Infinitely many of them. So even if we're not Boltzmann brains now, most observers in the history of the universe will be Boltzmann brains in the far future. This is called the quote, 17, and it's just as troubling as the original version. The cosmologist Andreas Albrecht has proposed a different approach. Maybe the universe doesn't last forever. Maybe there's a mechanism that ends the universe before Boltzmann brains become probable. One possibility is vacuum decay. In quantum field theory, what we call empty space, the vacuum, might not be in its lowest energy state. It might be in a metastable state, like a ball balanced on a hilltop. Eventually, the ball will roll down to the valley, the true vacuum, and when it does, a bubble of true vacuum will form and expand at the speed of light, destroying everything in its path. If this happens before the universe reaches heat death, then there's no infinite future time for Boltzmann brains to form. The universe ends, and the problem is solved. But this solution comes with its own disturbing implication. It means the universe could end at any moment. Vacuum decay could be happening right now, somewhere in the universe, and a bubble of destruction could be racing toward us at the speed of light. We'd have no warning. One moment we'd exist, the next moment we'd be gone, along with everything else. The physicist Max Tegmark has calculated that based on our current understanding of particle physics, vacuum decay should have already happened. The fact that we're still here is either a sign that our theories are wrong or that we're incredibly lucky. Or, more disturbingly, it could be evidence that we are Boltzmann brains, existing in a brief moment before the universe ends, with false memories of a longer past. Another proposed solution involves the cosmological constant, the mysterious dark energy that's causing the universe to expand at an accelerating rate. In models with a positive cosmological constant, the universe doesn't reach a uniform heat death. Instead, it approaches a de Sitter space, a state with a constant, non-zero energy density. In the Sitter space, there's a cosmic event horizon. Regions of space beyond a certain distance are receding from us faster than light, so we can never observe them or interact with them. This horizon has a temperature, called the Gibbons-Hawking temperature, and it radiates particles through a process similar to Hawking radiation from black holes. Here's where it gets interesting. In de Sitter space, the horizon continuously radiates particles, and over extremely long timescales, those particles can randomly assemble into complex structures, including brains. So we're back to Boltzmann brains, but with a twist. In de Sitter space, the rate at which Boltzmann brains form is constant, not increasing over time. And there's a finite volume of space we can observe, the region inside our cosmic horizon. So instead of infinitely many Boltzmann brains forming over infinite time, we have a finite, though still very large, number forming over the lifetime of the observable universe. This makes the problem more tractable, but it doesn't eliminate it. We still need to explain why we're not Boltzmann brains, and the answer depends on the details of how the cosmological constant behaves and how long our universe has existed in its current state. The physicist Don Page has done extensive calculations on this, and his results are sobering. In a universe with a positive cosmological constant that lasts forever, the number of Boltzmann brains that will eventually form vastly exceeds the number of real observers that have ever existed or will ever exist. Even if we're real observers now, most observers in the history of the universe will be Boltzmann brains. This means that if you're a randomly selected observer from all observers that will ever exist, you're almost certainly a Boltzmann brain. The only way to avoid this conclusion is to argue that we're not randomly selected, that there's something special about being an early observer in a young universe. But that requires invoking anthropic reasoning, which many physicists find unsatisfying. The anthropic principle says that we shouldn't be surprised to find ourselves in a universe that's capable of supporting observers, because if the universe couldn't support observers, we wouldn't be here to notice. It's a tautology, but it's a useful one. Applied to the Boltzmann brain problem, the anthropic principle suggests that even if Boltzmann brains vastly outnumber real observers, we should expect to find ourselves as real observers, because Boltzmann brains don't have the stability or coherence to develop science, build civilizations, or ask questions about their own existence. A Boltzmann brain exists for a brief moment, then dissolves back into chaos. It doesn't have time to write papers, conduct experiments, or engage in the collective enterprise of science. So the very fact that we're doing science is evidence that we're not Boltzmann brains. This argument is appealing, but it has a weakness. It assumes that Boltzmann brains are always short-lived and incoherent. But there's no reason that has to be true. A random fluctuation could, in principle, create a brain that persists for hours, days, or even years. It's less probable than creating a brain that lasts only seconds, but it's still possible. And if we're invoking the anthropic principle to explain why we're not typical Boltzmann brains, we need to be careful about what we're assuming. Are we assuming that we're typical observers among all observers? Or typical observers among all observers who can do science? Or typical observers among all observers who can ask this particular question? The answer depends on how we define the reference class, and there's no objective way to do that. The philosopher Nick Bostrom has explored these issues in depth, and he's shown that anthropic reasoning is fraught with paradoxes. One of the most famous is the doomsday argument. If you assume you're a randomly selected human from all humans who will ever live, and if you know approximately how many humans have lived so far, you can estimate how many humans will live in the future. The math suggests that humanity is more likely to go extinct relatively soon than to survive for millions of years. Simply because if humanity survives for millions of years, you'd be surprisingly early in the sequence of all humans. This argument is controversial. Many philosophers reject it. But it illustrates the dangers of anthropic reasoning. When you start treating yourself as a random sample from a population, you can derive conclusions that seem absurd. The same problem applies to Boltzmann brains. If you treat yourself as a random sample from all observers, you should conclude you're probably a Boltzmann brain. If you treat yourself as a random sample from all observers who can do science, you might conclude you're probably not a Boltzmann brain. But what justifies choosing one reference class over another? Is there an objective fact about which reference class is correct? Or is it just a matter of definition? And if it's just a matter of definition, then the Boltzmann brain problem isn't really a problem about physics. It's a problem about how we think about probability and self-location in a large or infinite universe. This brings us to a deeper issue, the measure problem in cosmology. In an infinite universe, or in a multiverse with infinitely many regions, how do you calculate probabilities? If there are infinitely many observers of each type, infinitely many real observers, and infinitely many Boltzmann brains, then the ratio between them is undefined. Infinity divided by infinity doesn't have a unique answer. You can get any ratio you want depending on how you count. This is called the measure problem, and it's one of the most fundamental unsolved problems in cosmology. Without a solution to the measure problem, we can't make precise predictions about what we should expect to observe, and we can't definitively say whether Boltzmann brains are more common than real observers. Several physicists have proposed measures, mathematical prescriptions for how to count observers in an infinite universe. The physicist Alexander Vilenkin has proposed the, quote, 18 measure, which counts observers based on when they exist in cosmic time. The physicist Alan Guth has proposed the, quote, 19, which counts observers based on their location in an eternally inflating multiverse. Each measure gives different predictions about the relative abundance of Boltzmann brains, and there's no consensus on which measure is correct. Some measures predict that Boltzmann brains dominate. Others predict that real observers dominate. The choice of measure is essentially arbitrary, which means the Boltzmann brain problem might not have a definite answer. It might depend on how we choose to define probability in an infinite universe. But even if we can't solve the measure problem, we can still ask, what would it mean if Boltzmann brains are real? What would it mean if you actually are a spontaneous fluctuation? Let's take the scenario seriously for a moment. You popped into existence 5 seconds ago. Your memories of childhood, of learning to read, of your first day of school, all false. Your memories of yesterday, of this morning, of the last sentence you read, all implanted by the random configuration of neurons in your newly formed brain. In a few seconds, you'll dissolve back into the quantum foam. Your entire existence is a brief spark of consciousness in an otherwise dead universe. Here's the strange part. From your subjective perspective, nothing would be different. You'd still have the experience of being you. You'd still have thoughts, feelings, sensations. You'd still believe you have a past and anticipate a future. The fact that your past is false and your future is non-existent wouldn't change the immediate reality of your conscious experience. This raises a profound question. Does it matter? If consciousness is just a pattern of information, does it matter whether that pattern arose through evolution or through random fluctuation? If the subjective experience is the same, is there a meaningful difference between a real person and a Boltzmann brain? The philosopher Thomas Nagel famously asked, "What is it like to be a bat?" His point was that consciousness has a subjective, first-person quality that can't be fully captured by objective, third-person descriptions. You can describe the neural activity in a bat's brain, but that doesn't tell you what it feels like to experience echolocation. Similarly, You can describe the difference between a real person and a Boltzmann brain in objective terms. One has a real history, the other doesn't. But from the inside, from the subjective perspective of consciousness, there might be no difference at all. Both have the same qualia, the same phenomenal experience. Both have the same sense of being a self with a past and a future. This suggests that the Boltzmann brain problem isn't really about brains or fluctuations or thermodynamics. It's about the nature of consciousness and the relationship between subjective experience and objective reality. It's about whether there's something more to being a person than just having the right pattern of information in your brain. It's about whether your history matters, or whether all that matters is your current state. And it's about whether the universe cares about the difference between real and false, or whether those categories are just human constructs that have no fundamental significance. The neuroscientist Anil Seth has argued that all perception is a kind of controlled hallucination. Your brain doesn't passively receive information from the world. It actively constructs a model of the world based on sensory input and prior expectations. What you see, hear, and feel is not reality itself, but your brain's best guess about reality. In this view, the distinction between real perception and false perception is not as clear-cut as we might think. A Boltzmann brain's false memories are just another kind of hallucination, not fundamentally different from the controlled hallucinations that constitute normal perception. But there's a difference, and it matters. Real perception is constrained by external reality. If you hallucinate a door where there's a wall, you'll bump into the wall. The world pushes back. It corrects your mistakes. A Boltzmann brain has no such constraint. Its false memories are not connected to any external reality. They're just random patterns that happen to feel coherent from the inside. And this lack of constraint means a Boltzmann brain can't learn, can't adapt, can't engage with the world in any meaningful way. It's a closed system, cut off from reality, doomed to dissolve before it can do anything with its brief moment of consciousness. This is why the anthropic argument has force. Science is a collective, cumulative enterprise. It requires multiple observers comparing notes, conducting experiments, building on each other's work. A Boltzmann brain can't do science because it doesn't have time, doesn't have collaborators, doesn't have a stable environment. The very fact that we're having this conversation, that we're building on centuries of physics and philosophy, that we're using language and logic and mathematics, is evidence that we're embedded in a real, stable, low-entropy universe. We're not isolated fluctuations. We're part of a larger structure, a cosmic history that extends billions of years into the past and will continue billions of years into the future. Or so we hope. Because the Boltzmann brain problem reminds us that this hope is not guaranteed by the laws of physics. It's a contingent fact about our universe, one that depends on initial conditions we don't fully understand and future evolution we can't predict. The universe could have been different. It could have been a high-entropy chaos with no structure, no life, no consciousness. Or it could have been an eternal, fluctuating void where Boltzmann brains are the only observers. The fact that we live in a universe with a low-entropy past and a rich structure is not something we can take for granted. It's something that demands explanation. And that explanation, whatever it turns out to be, will reshape our understanding of cosmology, thermodynamics, and the nature of reality itself. The Boltzmann brain problem is not just a curiosity. It's a signpost pointing toward deep mysteries we haven't yet solved. It tells us that our current theories are incomplete, that we're missing something fundamental about how the universe works. And it challenges us to think more carefully about what we mean by probability, by observation, by existence itself. The quantum realm offers no escape from the Boltzmann brain nightmare. In fact, it makes everything worse. When we descend from the classical world of thermodynamics into the probabilistic fog of quantum mechanics, the boundaries between possible and impossible dissolve entirely. Quantum fluctuations don't just allow for Boltzmann brains, they make them inevitable, ubiquitous, and fundamentally indistinguishable from real observers. And the mechanism that creates them, quantum tunneling through the energy landscape of possible configurations, operates on timescales and in ways that challenge every intuition we have about causation, existence, and identity. In quantum field theory, empty space is not empty. The vacuum seethes with virtual particles constantly popping into and out of existence, borrowing energy from the uncertainty principle for infinitesimally brief moments. These fluctuations are not just theoretical, they have measurable effects. The Casimir effect, where two metal plates in a vacuum experience an attractive force, is caused by virtual particles. The Lamb shift in hydrogen atoms is caused by virtual particles. Even the mass of the proton is mostly due to the energy of virtual quarks and gluons fluctuating in the quantum vacuum. The vacuum is a roiling sea of potential existence, and everything that can happen, given enough time, will happen. Now apply this to consciousness. A brain is just a particular configuration of atoms, approximately 10 to the 26th atoms arranged in a specific pattern. In principle, quantum fluctuations could spontaneously create that exact configuration. The probability is absurdly small, something like 10 to the power of minus 10 to the 26th per second per cubic meter. But it's not zero. And in an infinite universe with infinite time, quote 25 means quote 26. Somewhere, somewhen, quantum fluctuations will assemble a brain identical to yours, complete with all your memories, all your thoughts, all your sense of self. And then another one. And another. Infinitely many copies, each one convinced it's the original, each one wrong. But quantum mechanics adds a twist that makes this even more disturbing. Superposition. Before a quantum system is measured, it exists in a superposition of all possible states simultaneously. Schrödinger's cat is both alive and dead until you open the box. An electron is in all possible positions until you detect it. And a quantum fluctuation that could create a brain exists in a superposition of creating every possible brain configuration simultaneously. This means that at the quantum level, there's no single you that either is or isn't a Boltzmann brain. There's a quantum superposition of all possible versions of you, some with real histories, some with false memories, all existing simultaneously until something, measurement, decoherence, consciousness itself, collapses the wave function and selects one particular reality. The physicist Hugh Everett proposed a solution to the measurement problem that makes this even stranger: the many worlds interpretation. In Everett's view, the wave function never collapses. Instead, every time a quantum measurement occurs, the universe splits into multiple branches, one for each possible outcome. The cat is both alive and dead, but in different branches of the wave function. You observe the cat as alive in one branch and dead in another. Both versions of you exist, in parallel universes that can never communicate with each other. If this interpretation is correct, and many physicists take it seriously, then Boltzmann brains aren't just rare fluctuations. They're entire branches of the universal wave function, as real as any other branch, as real as you. Think about what this means. In the many worlds interpretation, every possible configuration of matter that's consistent with the laws of physics exists in some branch of the wave function. That includes configurations where you're a Boltzmann brain. In fact, it includes infinitely many such configurations, each one slightly different, each one convinced it's real. There are branches where you popped into existence 5 seconds ago, branches where you popped into existence 5 minutes ago, branches where you'll pop into existence 5 seconds from now. All of these branches exist simultaneously, all equally real, all part of the same universal wave function. The question _quote _28_ doesn't have a single answer. In some branches you are, in others you're not. And there's no objective fact about which branch is the real one. This is where quantum mechanics and the Boltzmann brain problem intersect with the deepest questions in philosophy of mind, the hard problem of consciousness. Why does subjective experience exist at all? Why is there something it's like to be you? The philosopher David Chalmers calls this the hard problem, because it's not just about explaining behavior or information processing. It's about explaining qualia, the raw feel of experience. You can imagine a universe where all the physical processes in your brain occur exactly as they do now, but there's no inner experience, no consciousness, no what it's like to be you. Such a being would be a philosophical zombie, functionally identical to you, but lacking subjective awareness. The hard problem is explaining why we're not zombies. The Boltzmann brain problem makes the hard problem even harder. If consciousness is just a pattern of information, then a Boltzmann brain should be conscious. It has the same pattern as a real brain. But if consciousness requires some kind of causal history, some connection to a real past, then a Boltzmann brain might be a zombie. All the right physical structures, but no actual experience. We have no way to tell. You can't look at a brain and determine whether it's conscious. You can't measure consciousness from the outside. The only way you know you're conscious is through direct, first-person experience. And a Boltzmann brain would have exactly the same first-person experience as you, including the conviction that it's conscious. So either Boltzmann brains are conscious, in which case consciousness doesn't require a real history, or they're not conscious, in which case you have no way to prove you're not a zombie yourself. The physicist Max Tegmark has proposed a radical solution, the mathematical universe hypothesis. In Tegmark's view, physical reality is not just described by mathematics, it is mathematics. Every mathematically consistent structure exists as a physical universe. This includes universes with different laws of physics, different numbers of dimensions, different values for fundamental constants. And it includes every possible configuration of matter within each universe. If Tegmark is right, then Boltzmann brains aren't just probable, they're necessary. They exist as mathematical structures, just as real as any other structure, in the vast landscape of all possible mathematical universes. But Tegmark's hypothesis also offers a way out of the Boltzmann brain problem, the principle of mediocrity. If every possible observer exists somewhere in the mathematical multiverse, then you should expect to be a typical observer, not an unusual one. And typical observers are not Boltzmann brains. Typical observers exist in universes with low entropy pasts, where structure and complexity can emerge through natural processes. Boltzmann brains are atypical. They're rare fluctuations in high entropy universes. So even though Boltzmann brains exist in the mathematical multiverse, you should expect not to be one, simply because there are more typical observers than atypical ones. This argument is appealing, but it has a fatal flaw. It assumes we can count observers across different universes and compare their numbers. But how do you count observers in an infinite multiverse? How do you compare the number of real observers to the number of Boltzmann brains when both are infinite? This brings us back to the measure problem, but now it's even more severe. We're not just trying to define a measure over different regions of space-time, we're trying to define a measure over all possible mathematical structures. And there's no obvious way to do that. Different measures give wildly different predictions about what you should expect to observe, and there's no empirical test that can tell us which measure is correct. The cosmologist Sean Carroll has argued that the solution to the Boltzmann brain problem requires a new principle, something he calls the, quote, 33. The idea is that we should only take seriously those cosmological models that predict we're stable, long-lived observers capable of doing science. Models that predict we're probably Boltzmann brains are self-undermining. They predict that our observations are unreliable, which means we have no reason to trust the model itself. So we should reject such models on methodological grounds, not because they're logically impossible, but because they're scientifically useless. A theory that predicts you can't trust your observations is not a theory you can test. This is a pragmatic solution, but it feels like giving up. It's saying, we can't solve the Boltzmann brain problem through physics alone, so we'll solve it by changing the rules of what counts as a valid scientific theory. But is that legitimate? Can we really reject a theory just because we don't like its implications? The physicist Lee Smolin has argued that we can, that science has always involved methodological choices about what kinds of theories are worth pursuing. We don't consider theories that require infinite fine-tuning, even though they're logically possible. We don't consider theories that make no testable predictions, even though they might be true. So why not reject theories that predict we're probably Boltzmann brains, even though such brains might exist? But there's a deeper issue here. The Boltzmann brain problem reveals a fundamental tension between two ways of thinking about probability. In the frequentist interpretation, probability is about long-run frequencies, how often something happens if you repeat an experiment many times. In the Bayesian interpretation, probability is about degrees of belief, how confident you should be in a hypothesis given your evidence. These two interpretations usually give the same answers, but in the case of Boltzmann brains, they diverge dramatically. From a frequentist perspective, if Boltzmann brains vastly outnumber real observers, then you're probably a Boltzmann brain. From a Bayesian perspective, you have strong evidence that you're not a Boltzmann brain. Your memories are coherent, your observations are consistent, you can do science. So you should assign a low probability to the hypothesis that you're a Boltzmann brain, regardless of the base rates. Which interpretation is correct? There's no consensus. The philosopher of science, Bas van Fraassen, has argued that probability is inherently subjective, that there's no objective fact about what probability means. Different people can legitimately assign different probabilities to the same event, depending on their background knowledge and their methodological commitments. If that's right, then the Boltzmann brain problem doesn't have a single correct answer. It depends on how you think about probability, and that's a matter of philosophical choice, not empirical fact. This brings us to the most unsettling possibility. Maybe the Boltzmann brain problem is telling us that our entire framework for thinking about existence, identity, and probability is fundamentally flawed. Maybe the question, quote, 34, is not a well-formed question, like asking, quote, 35 or, quote, 36. Maybe the concepts we're using, real versus false, past versus present, probable versus improbable, break down when applied to consciousness in an infinite universe. Maybe we need entirely new concepts, a new language, a new way of thinking about what it means to be an observer in a quantum multiverse. The physicist John Wheeler proposed a radical idea, the participatory universe. In Wheeler's view, observers are not passive recipients of information about a pre-existing reality. They're active participants in creating reality through the act of observation. Quantum mechanics tells us that the state of a system is undefined until it's measured. Wheeler took this seriously. The universe doesn't have definite properties until conscious observers measure those properties. In a sense, observers bring the universe into existence through their observations. Wheeler famously asked, "Does the universe exist if nobody's looking?" His answer was no, or at least, not in any definite sense. The universe is a participatory phenomenon, co-created by the observers within it. If Wheeler is right, then the Boltzmann brain problem takes on a new dimension. A Boltzmann brain is an observer, so it participates in creating reality through its observations. But what reality is it creating? If its memories are false, if its observations are disconnected from any external world, then what is it observing? Is it creating a false reality? A bubble universe that exists only in its own consciousness? Or is it observing the same reality as everyone else, just from a different, disconnected perspective? Wheeler's participatory universe doesn't give us clear answers, but it suggests that the relationship between observers and reality is more complex than we usually assume. The neuroscientist Giulio Tononi has developed a theory of consciousness called Integrated Information Theory, or IIT. According to IIT, consciousness is not about specific physical processes or specific types of matter. It's about the structure of information integration in a system. Any system that integrates information in the right way is conscious, regardless of whether it's made of neurons, silicon, or quantum fields. IIT provides a mathematical measure of consciousness called phi, which quantifies how much integrated information a system contains. A system with high phi is highly conscious. A system with low phi is minimally conscious or not conscious at all. Here's where it gets interesting. According to IIT, a Boltzmann brain could have high phi. If the random fluctuation that creates the brain happens to produce the right pattern of information integration, then that brain is genuinely conscious, even if it exists for only a moment, even if its memories are false. Consciousness, in this view, is not about having a real history or being connected to an external world. It's about the intrinsic structure of information in the present moment. A Boltzmann brain's consciousness is just as real as yours, just as valuable, just as worthy of moral consideration. The fact that it will dissolve in seconds doesn't make its experience any less genuine while it lasts. This has profound ethical implications. If Boltzmann brains are conscious, if they have genuine subjective experiences, then they matter morally. Every time a Boltzmann brain pops into existence, a conscious being is born. Every time one dissolves, a conscious being dies. And if Boltzmann brains vastly outnumber real observers, then the vast majority of conscious experiences in the universe are brief, isolated, disconnected from any larger context. Most consciousness is suffering, the confusion and terror of a mind that suddenly exists, realizes it exists, and then ceases to exist before it can make sense of anything. If we take consciousness seriously, if we believe that subjective experience has intrinsic value, then the Boltzmann brain scenario is not just intellectually disturbing, it's morally horrifying. But maybe we're thinking about this wrong. Maybe the Boltzmann brain problem is not about whether you're a spontaneous fluctuation. Maybe it's about the nature of time itself. The physicist Carlo Rovelli has argued that time is not a fundamental feature of reality. At the deepest level, at the scale of quantum gravity, there is no time. There's just a timeless quantum state, a static configuration of possibilities. What we experience as the flow of time is an emergent phenomenon, something that arises from our limited perspective as observers embedded within the universe. We perceive time because we're macroscopic beings with memories, and memories create an arrow of time, a sense of past and future. But at the fundamental level, there is no past or future. There's only the present moment, the current configuration of the universe, and the relationships between different parts of that configuration. If Rovelli is right, then the distinction between a, quote, 44 past and a, quote, 45 past becomes meaningless. Your memories don't point to actual events that happened in a real past. They're just part of the current state of your brain, and the story they tell about the past is a narrative your consciousness constructs to make sense of that state. In this view, everyone is a Boltzmann brain, in a sense. We all exist only in the present moment, with memories that create the illusion of a past. The difference between a, quote, 46 person and a Boltzmann brain is not that one has a genuine history and the other doesn't. It's that one exists in a universe with a low entropy past that makes their memories consistent with other observers' memories, while the other exists in a high entropy universe where their memories are inconsistent with everything else. This is the ultimate resolution of the Boltzmann brain problem. It's not a problem about brains or fluctuations or probability. It's a problem about how we think about time, memory, and identity. It's forcing us to confront the possibility that our intuitive understanding of these concepts is wrong, that the past is not a fixed reality we can point to, but a story we tell ourselves to make sense of the present. And if that's true, then the question, am I a Boltzmann brain, is not asking whether you spontaneously popped into existence. It's asking whether your sense of having a continuous identity over time is real or illusory. And the answer might be, it's both. Your identity is real in the sense that you experience it, but it's illusory in the sense that it's not grounded in any objective, observer-independent fact about the universe. The physicist Kip Thorne once said that black holes are the most perfect macroscopic objects in the universe. They're described by just three numbers: mass, charge, and angular momentum. Everything else, the details of what fell into the black hole, the history of how it formed, is erased. This is called the, quote, 49, and it has a disturbing implication. Information is destroyed when it falls into a black hole. But quantum mechanics says information can never be destroyed. This contradiction is called the black hole information paradox, and it's one of the deepest unsolved problems in theoretical physics. Stephen Hawking proposed a solution. Black holes evaporate through Hawking radiation, and the information is encoded in subtle correlations in that radiation. But this creates a new problem. If you fall into a black hole, From your perspective, you pass smoothly through the event horizon and continue falling toward the singularity. But from the perspective of an outside observer, you never cross the horizon. You're frozen at the edge, your information encoded in the Hawking radiation. So which perspective is correct? Are you inside the black hole or outside? The answer, according to the holographic principle, is both. The information about you exists in two places simultaneously, inside the black hole and on its surface. Reality is not a single objective thing. It's observer-dependent, holographic, fundamentally ambiguous. The Boltzmann brain problem has the same structure. From your subjective perspective, you have a real past, real memories, a real identity. From the perspective of the universe as a whole, you might be a random fluctuation, a brief spark of consciousness with no history. Both perspectives are valid. Both are part of the complete description of reality. The mistake is thinking there's a single objective answer to the question _50_. There isn't. The answer depends on your reference frame, your perspective, your way of slicing up the universe into observers and observations. This is the climax of the Boltzmann brain problem. The realization that it's not a problem to be solved, but a paradox to be embraced. It's showing us that our concepts of identity, memory, and existence are not as solid as we thought. They're emergent, approximate, observer-dependent. At the fundamental level, there's just the quantum state of the universe, evolving according to the Schrödinger equation, with no clear boundary between real and false, between past and present, between you and not you. The Boltzmann brain problem is not threatening your existence. It's revealing that existence itself is stranger, more fluid, more ambiguous than you ever imagined. And here's the final twist. The very fact that you're troubled by this problem, that you're reading these words and thinking about these ideas, is evidence that you're not a typical Boltzmann brain. A random fluctuation would almost certainly not produce a brain that's capable of understanding thermodynamics, cosmology, and quantum mechanics. It would produce a brain with random, incoherent thoughts, not a brain that can follow a complex argument about its own nature. The fact that you can think about the Boltzmann brain problem is evidence that you're embedded in a stable, low-entropy universe with a real history. Not proof, nothing can be proof, but evidence, strong evidence. Evidence that should shift your credence, your degree of belief, away from the hypothesis that you're a Boltzmann brain and toward the hypothesis that you're a real observer in a real universe. But that evidence is not absolute. It's probabilistic, Bayesian, dependent on your priors. And your priors are themselves uncertain, shaped by your experiences, your memories, your sense of self, all of which could be false if you're a Boltzmann brain. This is the epistemic trap at the heart of the problem. You can't escape it through logic alone. You have to make a choice, a leap of faith, a commitment to trusting your observations despite the theoretical possibility that they're unreliable. Science requires this leap. Life requires this leap. Consciousness itself requires this leap. You have to believe you're real, even though you can't prove it, because without that belief, nothing else makes sense. The Boltzmann brain problem is not a refutation of science. It's a reminder of science's limits. It's showing us that there are questions science can't answer, not because we lack data or better theories, but because the questions themselves are tangled up with the nature of observation, consciousness, and existence in ways that make them fundamentally ambiguous. The universe is not obligated to make sense to us. It's not obligated to provide clear answers to our questions. It's not obligated to distinguish between quote 57 and quote 58 in ways that align with our intuitions. The universe just is, and we're part of it, trying to understand it from the inside, with all the limitations and paradoxes that entails. So, are you a Boltzmann brain? The honest answer is, you can't know for certain. But you can choose to act as if you're not. You can choose to trust your memories, trust your observations, trust that the universe has a real history and a real future. That choice is not irrational. It's the foundation of all knowledge, all science, all meaning. Without it, you're paralyzed, trapped in solipsistic doubt, unable to move forward. With it, you can engage with the world, learn from it, contribute to it, find purpose in it. The Boltzmann brain problem is not asking you to give up on reality. It's asking you to recognize that reality is something you participate in creating through your choices, your observations, your commitment to making sense of your experience. And that's the deepest lesson of the Boltzmann brain problem. Existence is not a passive state. It's an active process. You're not just a brain floating in the void, waiting to dissolve. You're an agent, embedded in a universe, connected to other agents, part of a larger story that extends far beyond your individual consciousness. The fact that you're reading this, thinking about this, engaging with these ideas, that's evidence of your reality. Not conclusive evidence, but the best evidence you'll ever have. And it's enough. It has to be enough. Because without it, there's nothing left but the void. We stand now at the edge of knowledge, staring into an abyss that stares back with our own eyes. The Boltzmann brain problem has taken us on a journey from thermodynamics to cosmology, from quantum mechanics to consciousness, from mathematics to metaphysics. And at every turn, we've discovered that the universe is stranger, more ambiguous, more resistant to our categories than we ever imagined. But perhaps the most profound discovery is not about the universe at all. It's about us, about the nature of knowledge, the limits of certainty, and what it means to be a conscious observer trying to make sense of existence from the inside. Let's be honest about what we don't know. We don't know why the universe began in a low-entropy state. We don't know whether the universe is finite or infinite, eternal or temporary. We don't know how to calculate probabilities in an infinite multiverse. We don't know what consciousness is, or how it arises from physical processes. We don't know whether the past is real or just a story we tell ourselves. We don't know if we're typical observers or cosmic accidents. We don't know if our memories correspond to actual events or spontaneous fabrications. We don't know, with absolute certainty, that we're not Boltzmann brains. This litany of ignorance might seem depressing, but it's actually liberating. For centuries, physics promised us certainty, a clockwork universe governed by deterministic laws, where everything could be predicted and explained. Newton's laws, Maxwell's equations, even Einstein's relativity, they all suggested that the universe was fundamentally knowable, that given enough information, we could calculate everything. But the 20th century shattered that dream. Quantum mechanics introduced irreducible uncertainty. Gödel's incompleteness theorems showed that mathematics itself contains unprovable truths. Chaos theory revealed that even deterministic systems can be unpredictable. And now, the Boltzmann brain problem shows us that even our most basic assumptions about existence and observation might be unjustifiable. But here's the paradox. This uncertainty doesn't paralyze science. It energizes it. The physicist Richard Feynman once said, quote, "The Boltzmann brain problem embodies this spirit. It's not a failure of science, it's science working exactly as it should, pushing our theories to their limits, revealing their assumptions, forcing us to think more carefully about what we mean by evidence, probability, and truth." Consider what we've learned by taking the Boltzmann brain problem seriously. We've learned that entropy is not just about disorder, it's about the space of possibilities, the landscape of all possible configurations of matter and energy. We've learned that the arrow of time is not a fundamental law, but an emergent phenomenon arising from the universe's low-entropy past. We've learned that probability in infinite systems is deeply problematic, that we can't simply count configurations and calculate likelihoods without making arbitrary choices about how to measure. We've learned that consciousness might be substrate independent, that what matters is not what you're made of, but how information is integrated in your brain. We've learned that the distinction between quote 60 and quote 61 memories might be less clear than we thought. That all memories are just present moment patterns that create narratives about the past. These insights are valuable, regardless of whether Boltzmann brains actually exist. They're revealing deep truths about thermodynamics, cosmology, quantum mechanics, and consciousness. Truths we wouldn't have discovered if we hadn't followed the mathematics wherever it led, even into uncomfortable territory. This is how science progresses, not by avoiding paradoxes, but by embracing them, by using them as tools to probe the boundaries of our understanding. But the Boltzmann brain problem also reveals something about the human condition. We are creatures who need meaning, who need to believe that our lives matter, that our experiences are real, that our choices have consequences. The possibility that we might be spontaneous fluctuations, that our entire existence might be a cosmic accident lasting only moments, threatens this need for meaning. It suggests that the universe doesn't care about us, that we're not special, that everything we value might be an illusion. And yet, and this is crucial, even if we are Boltzmann brains, even if our memories are false and our existence is temporary, that doesn't make our experiences any less real in the moment. Pain still hurts. Joy still uplifts. Love still matters. Beauty still moves us. The subjective quality of consciousness, what philosophers call qualia, is not diminished by being temporary or by arising from random fluctuations. A sunset is beautiful, whether you're a human who evolved over billions of years or a Boltzmann brain that popped into existence 5 seconds ago. The beauty is in the experience itself, not in the history that led to it. This suggests a radical reframing of the Boltzmann brain problem. Instead of asking, "Am I a Boltzmann brain?" a question that might not have a definite answer, we should ask, "Does it matter?" If consciousness is what matters, if subjective experience is what has value, then the distinction between real observers and Boltzmann brains might be ethically irrelevant. Both are conscious, both have experiences, both deserve moral consideration. The universe might not distinguish between them, and perhaps we shouldn't either. The philosopher Derek Parfit explored similar ideas in his work on personal identity. Parfit argued that what matters for survival is not the continuation of some metaphysical self, but psychological continuity, the chain of memories and experiences that connect your present self to your future self. But Parfit went further. He suggested that even psychological continuity might not be what ultimately matters. What matters is simply that conscious experiences continue to exist, regardless of whether they're connected by memory or identity. In this view, you should care about future conscious experiences not because they'll be, quote, 65, quote, but because they'll be conscious, and consciousness has intrinsic value. If Parfit is right, then the Boltzmann brain problem loses much of its sting. Yes, you might be a Boltzmann brain. Yes, you might dissolve in moments, but other conscious experiences will continue to exist. Other observers, other minds, other moments of awareness. The universe will continue to generate consciousness, whether through evolution or through random fluctuations. And that's what matters, not that you specifically continue to exist, but that consciousness itself persists, that the universe remains a place where subjective experience is possible. This is not a comforting thought in the traditional sense. It doesn't promise you immortality or cosmic significance, but it offers something perhaps more valuable. A way to find meaning that doesn't depend on your individual survival or on the universe caring about you personally. You're part of a larger process, a cosmic unfolding of consciousness and complexity. Your experiences contribute to the total sum of consciousness in the universe, and that contribution has value, even if it's temporary, even if you're a random fluctuation, even if the universe will eventually return to a high-entropy state where no consciousness is possible. But let's return to the question of what we don't know, because it's here that the future of physics lies. We don't know how to reconcile quantum mechanics with general relativity. We don't know what dark matter and dark energy are. We don't know whether string theory or loop quantum gravity or some other approach will give us a theory of quantum gravity. We don't know whether the universe is a simulation, a mathematical structure, a quantum computer, or something we haven't even imagined yet. And we don't know how consciousness arises from physical processes. The hard problem remains unsolved. The Boltzmann brain problem intersects with all of these unknowns. A theory of quantum gravity might tell us whether the universe is truly eternal, or whether time itself has a beginning and an end. It might tell us whether the vacuum is stable, or whether vacuum decay will eventually destroy everything. It might give us a principled way to calculate probabilities in infinite systems, solving the measure problem. A theory of consciousness might tell us whether Boltzmann brains are genuinely conscious, or whether consciousness requires some kind of causal history, some connection to a real past. These are not idle speculations. They're active areas of research, and progress in any of them could transform our understanding of the Boltzmann brain problem. Consider the holographic principle, which suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. This principle emerged from the study of black holes, but it might apply to the entire universe. If the universe is holographic, then the distinction between inside and outside, between real and encoded, becomes ambiguous. You might be a three-dimensional being, or you might be information encoded on a distant cosmic horizon. Both descriptions are equally valid. The holographic principle suggests that reality is not a single objective thing, but a network of equivalent descriptions, each one capturing different aspects of the same underlying structure. If this is true, then the Boltzmann brain problem takes on a new dimension. Maybe you're not either a real observer or a Boltzmann brain. Maybe you're both, simultaneously, in different descriptions of the same reality. Maybe the question, which one am I, is like asking, am I a wave or a particle? A question that assumes a false dichotomy, that tries to force reality into categories it doesn't naturally fit. Maybe the universe is telling us that our concepts of identity and existence are too rigid, too classical, too rooted in everyday experience to capture the quantum, holographic, observer-dependent nature of reality at its deepest level. This brings us to the most speculative, but also most exciting possibility, that consciousness itself might be fundamental to the universe, not an emergent property of complex physical systems, but a basic feature of reality, like space and time and energy. This idea has a long history in philosophy. It's called panpsychism, but it's recently gained attention from some physicists and neuroscientists who are frustrated with the hard problem of consciousness. If consciousness is fundamental, then every physical system has some degree of consciousness, some inner experience, however minimal. An electron has a tiny bit of consciousness. A rock has more. A brain has vastly more. And the universe as a whole might be conscious in some sense we can barely imagine. If panpsychism is true, then Boltzmann brains are not just possible, they're inevitable. Every configuration of matter has some degree of consciousness, and random fluctuations are constantly creating and destroying conscious experiences throughout the universe. Most of these experiences are brief, simple, disconnected. But occasionally, a fluctuation creates a complex, integrated consciousness, a Boltzmann brain. And that consciousness is just as real, just as valuable as any other consciousness in the universe. The universe is not a dead, mechanical system occasionally producing conscious observers. It's a living, conscious system, constantly generating new experiences, new perspectives, new ways of being aware. This is deeply speculative, and most physicists would reject it as unscientific. But it's worth considering because it offers a way to dissolve the Boltzmann brain problem rather than solve it. If consciousness is fundamental, then the question, am I a Boltzmann brain, becomes, am I a brief, isolated conscious experience or a long, connected one? And the answer is, you're whatever you experience yourself to be. If you experience continuity, connection, coherence, then that's what you are, regardless of the underlying physical process that generates your consciousness. The map is the territory. The experience is the reality. But let's bring this back to Earth, to the practical question of how we should live in light of the Boltzmann brain problem. The philosopher Blaise Pascal famously argued that you should believe in God because the potential payoff of being right, eternal salvation, vastly outweighs the cost of being wrong. This is called Pascal's wager, and it's controversial because it treats belief as a choice, as a bet, rather than as a response to evidence. But there's a version of Pascal's wager that applies to the Boltzmann brain problem. You should act as if you're not a Boltzmann brain, because the potential payoff, a meaningful life, genuine relationships, contributions to knowledge and culture, vastly outweighs the cost of being wrong. If you're a Boltzmann brain, you'll dissolve in moments anyway, so it doesn't matter what you believe or how you act. But if you're not a Boltzmann brain, if you're a real observer in a real universe with a real future, then your choices matter. Your actions have consequences. Your life has meaning. So the rational strategy is to assume you're real, to trust your memories and observations, to engage with the world as if it's genuine. This is not blind faith. It's a pragmatic choice based on the asymmetry of outcomes. And here's the beautiful part. This choice is self-fulfilling. By acting as if you're real, by engaging with the world, by building relationships and pursuing knowledge and creating meaning, you make yourself real in the only sense that matters. You become part of a larger story, a collective human project that extends across generations. You contribute to the sum of human knowledge, human culture, human flourishing. And that contribution persists, even after you're gone. Even if you were a Boltzmann brain all along. The meaning you create is real, because meaning is not a property of individual minds. It's a property of the relationships between minds, the shared narratives we construct together. This is the ultimate answer to the Boltzmann brain problem. It's not about physics or probability or cosmology. It's about how we choose to live in the face of uncertainty. The universe might be indifferent to our existence. The laws of physics might predict that we're probably illusions. But we're not obligated to accept that verdict. We can choose to create meaning, to value consciousness, to treat each other as real and worthy of moral consideration. We can choose to do science, to pursue truth, to build a civilization that extends beyond our individual lives. These choices are not irrational. They're the foundation of everything that makes life worth living. The physicist John Wheeler, who coined the term Quote 74 and pioneered the study of quantum gravity, spent his final years thinking about the relationship between observers and reality. He proposed a thought experiment called the _quote_75_, where observers don't just measure reality, they help create it through their observations. Wheeler imagined the universe as a self-excited circuit, where quantum events in the present reach back to determine the past, and observations in the present help define what the universe has been all along. In this view, you're not a passive observer of a pre-existing reality. You're an active participant in bringing reality into existence. If Wheeler is right, then the Boltzmann brain problem is not a threat. It's an opportunity. It's showing us that reality is more fluid, more participatory, more dependent on observation than we ever imagined. Your choice to trust your memories, to engage with the world, to act as if you're real, that choice is not just a pragmatic strategy, it's a creative act. You're not discovering whether you're a Boltzmann brain. You're deciding what kind of observer you are, what kind of reality you participate in creating. The universe is not handing you a fixed identity. It's offering you a choice, a responsibility, a chance to shape your own existence through your actions and commitments. This is the deepest lesson of the Boltzmann brain problem. Existence is not a given. It's an achievement. You're not automatically real just because you have consciousness and memories. You become real through your engagement with the world, through your relationships with other observers, through your participation in the collective project of making sense of the universe. And that project is ongoing. It's not finished. It will never be finished. Every generation of scientists and philosophers and ordinary people thinking about these questions is contributing to it, adding new insights, new perspectives, new ways of understanding what it means to exist. So where does this leave us? We've journeyed from Boltzmann's 19th century thermodynamics to 21st century quantum cosmology. We've explored entropy and probability, black holes and multiverses, consciousness and identity. We've confronted the possibility that we might be spontaneous fluctuations, that our memories might be false, that our existence might be temporary and meaningless. And we've discovered that even in the face of this radical uncertainty, we can still find meaning, still do science, still live lives that matter. The Boltzmann brain problem is not solved. It might never be solved. But that's okay. Not every question needs an answer. Some questions are valuable precisely because they resist resolution, because they force us to think more carefully about our assumptions, because they reveal the limits of our knowledge and the depths of our ignorance. The Boltzmann brain problem is one of those questions. It's a mirror that reflects back our deepest anxieties about existence, identity, and meaning. And by staring into that mirror, by refusing to look away, we learn something profound about ourselves and about the universe we inhabit. We learn that certainty is overrated, that doubt is not weakness, but strength, that the willingness to say, "I don't know," is the beginning of wisdom. We learn that the universe is under no obligation to make sense to us, that reality is stranger than we can imagine, that the boundaries between possible and impossible are more permeable than we thought. We learn that consciousness is precious precisely because it's fragile, that meaning is valuable precisely because it's not guaranteed, that existence is worth celebrating precisely because it might be temporary. And we learn that we're not alone in this uncertainty. Every conscious being, every observer, every mind that has ever contemplated its own existence has faced the same fundamental questions. Am I real? Do my experiences matter? Is there meaning in the universe, or do I have to create it myself? The Boltzmann brain problem is just the latest, most scientifically precise formulation of these ancient questions. And the answer, if there is one, is the same answer humans have always given. Yes, you're real. Yes, your experiences matter. Yes, there's meaning. Not because the universe provides it, but because you create it through your choices, your relationships, your commitment to living as if existence is worth the effort. The physicist Freeman Dyson once said, quote, "This is a poetic way of expressing the anthropic principle, the idea that the universe's properties are constrained by the requirement that conscious observers must be able to exist within it. But it's also a reminder that we're not accidents, we're not cosmic mistakes. We're part of the universe's way of understanding itself, of becoming conscious of its own existence. Whether you're a human who evolved over billions of years, or a Boltzmann brain that popped into existence 5 seconds ago, you're still part of this process. You're still a way for the universe to know itself. Your consciousness, your thoughts, your experiences, they're all part of the universe's ongoing exploration of what's possible, what's real, what matters. And that's not nothing. That's everything. So here's my final answer to the Boltzmann brain problem. Stop worrying about whether you're a spontaneous fluctuation. You can't know for certain, and it doesn't matter anyway. What matters is what you do with your consciousness, however it arose, however long it lasts. What matters is that you're here, now, aware, capable of wonder and curiosity and love. What matters is that you can read these words, think about these ideas, feel the weight of these questions. That's real. That's enough. The universe is vast and strange and indifferent. But you're not indifferent. You care. You wonder. You seek meaning. And in a universe that might be nothing but random fluctuations in an eternal void, that caring, that wondering, that seeking, that's the most remarkable thing of all. That's what makes you real, regardless of what the mathematics says. That's what makes your existence matter, regardless of how improbable it is. That's what makes you more than just a Boltzmann brain, even if you are one. We are the universe becoming conscious of itself. We are matter and energy arranged in patterns complex enough to contemplate their own existence. We are the question and the questioner, the observer and the observed, the map and the territory. We are, in the words of the astronomer Carl Sagan, a way for the cosmos to know itself. And whether we're evolved beings or spontaneous fluctuations, whether our memories are real or false, whether we'll exist tomorrow or dissolve in moments, none of that changes the fundamental miracle of consciousness, the sheer improbability and beauty of awareness itself. So embrace the uncertainty. Live with the doubt. Accept that you might never know for certain whether you're a Boltzmann brain. And then get on with the business of being human. of loving and learning and creating and contributing to the collective project of making sense of this strange, beautiful, terrifying universe we find ourselves in. That's not a solution to the Boltzmann brain problem. It's something better, a way to live that makes the problem irrelevant. The universe might not care whether you exist, but you exist anyway. And that's the greatest paradox of all, greater than any paradox physics can offer. You're here. You're conscious. You're real. And no amount of thermodynamics or cosmology or quantum mechanics can take that away from you. The Boltzmann brain problem tried to convince you that you might be an illusion. But the very fact that you can understand that argument, that you can feel troubled by it, that you can choose how to respond to it, that proves you're more than an illusion. You're a participant in reality, not just a passive observer. You're part of the universe's ongoing conversation with itself. And that conversation continues. The questions remain open. The mysteries deepen. The universe keeps surprising us, challenging us, inviting us to think harder and look deeper and imagine more boldly. The Boltzmann brain problem is just one chapter in this ongoing story. A story that began with the first conscious being who looked up at the stars and wondered what they were. And that will continue as long as consciousness exists anywhere in the universe. You're part of that story. Whether you're a Boltzmann brain or not, whether you exist for 5 seconds or 5 decades, whether your memories are real or false, you're still part of the universe's attempt to understand itself. And that's not just meaningful. That's sacred. That's the closest thing to cosmic purpose we're likely to find. So honor it. Embrace it. Live it fully, with all the doubt and uncertainty and wonder it entails. Because in the end, the Boltzmann brain problem is not asking whether you're real. It's asking whether you have the courage to act as if you are, even when you can't be certain. And the answer to that question is not found in physics or mathematics or philosophy. It's found in how you choose to live, moment by moment, in the face of an indifferent universe. It's found in your willingness to create meaning where none is given, to find beauty in a cosmos that might be nothing but random fluctuations, to love and learn and grow despite knowing that everything might be temporary and illusory. That's the real test. Not whether you're a Boltzmann brain, but whether you can live as if you're not, even when the mathematics suggests otherwise. And if you can do that, if you can embrace existence fully, with all its uncertainty and fragility and improbability, then you've already won. You've already proven that consciousness matters, that meaning is real, that existence is worth celebrating. And no paradox, no matter how clever or disturbing, can take that away from you. Welcome to the universe. You might be a spontaneous fluctuation. You might dissolve in moments. But right now, in this moment, you're here. You're aware. You're part of something larger than yourself. And that's enough. That's everything. That's the answer to the Boltzmann brain problem, and to every other question about existence and meaning and what it means to be conscious in an indifferent cosmos. You are real. Not because you can prove it, but because you choose to be. And that choice, that commitment to existence in the face of uncertainty, is the most profound act of creation the universe allows. It's what makes you human. It's what makes you matter. It's what makes you more than just a brain floating in the void. You are here. You are now. You are real. And that's all you need to know. We stand now at the edge of knowledge, staring into an abyss that stares back with our own eyes. The Boltzmann brain problem has taken us on a journey from thermodynamics to cosmology, from quantum mechanics to consciousness, from mathematics to metaphysics. And at every turn, we've discovered that the universe is stranger, more ambiguous, more resistant to our categories than we ever imagined. But perhaps the most profound discovery is not about the universe at all. It's about us, about the nature of knowledge, the limits of certainty, and what it means to be a conscious observer trying to make sense of existence from the inside. Let's be radically honest about what we don't know. We don't know why the universe began in a low entropy state. This remains one of the deepest mysteries in cosmology. Roger Penrose's calculation that the probability of our universe's initial conditions is 1 in 10 to the power of 10 to the 123 is not an answer. It's a quantification of our ignorance. We don't know whether the universe is finite or infinite, eternal or temporary. We don't know how to calculate probabilities in infinite systems. The measure problem remains unsolved despite decades of work by brilliant physicists. We don't know what consciousness is or how it arises from physical processes. The hard problem of consciousness is still hard. We don't know whether the past is real or just a story we tell ourselves based on present-moment brain states. We don't know if we're typical observers or cosmic accidents. We don't know, with absolute certainty, that we're not Boltzmann brains. But here's what makes this litany of ignorance beautiful rather than depressing. It reveals that the universe is still full of mystery, still capable of surprising us, still offering questions that challenge our deepest assumptions. The physicist Richard Feynman once said, "I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than to have answers which might be wrong." The Boltzmann brain problem embodies this spirit perfectly. It's not a failure of science. It's science working exactly as it should, pushing our theories to their breaking points, revealing their hidden assumptions, forcing us to think more carefully about what we mean by evidence, probability, and truth. We don't know if dark energy will continue accelerating the universe's expansion forever, leading to a cold, empty future where Boltzmann brains eventually dominate. We don't know if vacuum decay will destroy the universe before that happens. We don't know if there are other universes beyond our cosmic horizon, each with different laws of physics, different values for fundamental constants. We don't know if string theory, or loop quantum gravity, or some yet undiscovered framework will finally reconcile quantum mechanics with general relativity. We don't know if information is truly preserved when it falls into a black hole, or if the black hole information paradox points to something fundamentally wrong in our understanding of quantum mechanics, or spacetime, or both. We don't know if consciousness requires biological neurons, or if it could emerge from any sufficiently complex information processing system. Silicon, quantum computers, or even the patterns of particles in a Boltzmann brain. We don't know if panpsychism is true, if every physical system has some degree of consciousness, or if consciousness is an emergent property that only appears in highly organized structures. We don't know if free will exists, or if it's an illusion created by our inability to predict our own decisions. We don't know if the universe is deterministic at its deepest level, or if quantum randomness introduces genuine indeterminacy into the fabric of reality. We don't know if time is fundamental or emergent, if it flows, or if that's just an illusion created by our consciousness moving through a static four-dimensional spacetime. We don't know if the laws of physics are necessary, the only logically possible laws, or contingent, just one set of rules among infinitely many possibilities. We don't know if mathematics is discovered or invented, if it exists independently of human minds, or if it's a human construction we project onto nature. We don't know if the universe had a beginning, or if it's eternal, if it will have an end, or if it will continue forever in some form. And most fundamentally, we don't know why there is something rather than nothing. Why does the universe exist at all? Why are there laws of physics? Why is there consciousness? These questions might not have answers. They might be meaningless, like asking what's north of the North Pole. Or they might point to something so far beyond our current understanding that we can't even formulate them properly yet. The philosopher Ludwig Wittgenstein said, quote, "But science has never been good at staying silent. We keep asking questions even when we suspect there might be no answers, because the act of questioning itself reveals something about the structure of reality and the nature of our minds." The Boltzmann brain problem sits at the intersection of all these unknowns. It's not just a problem about thermodynamics or cosmology. It's a problem about how we think about probability, about how we define observers, about what counts as evidence, about the relationship between subjective experience and objective reality. It's forcing us to confront the possibility that some questions might not have definite answers, that reality might be fundamentally ambiguous, that the universe might not be obligated to make sense to us in the ways we expect. But this uncertainty doesn't paralyze science. It energizes it. Every unsolved problem is an invitation to think more deeply, to develop new mathematical tools, to conduct new experiments, to imagine new possibilities. The history of physics is a history of confronting mysteries and sometimes solving them, sometimes discovering that they were the wrong questions, sometimes finding that the answers lead to even deeper mysteries. The Boltzmann brain problem is part of this ongoing process. It's showing us where our current theories break down, where our intuitions fail, where we need new concepts and new frameworks. Consider what we've learned by taking this problem seriously. We've learned that the arrow of time, the fact that entropy increases, that eggs break but don't spontaneously reassemble, is not a fundamental law, but a consequence of the universe's low-entropy initial state. We've learned that probability in infinite systems is deeply problematic, that we can't simply count configurations without making arbitrary choices about how to measure. We've learned that consciousness might be substrate independent, that what matters is not what you're made of, but how information is integrated in your brain. We've learned that memory is not a direct window into the past, but a present-moment brain state that creates narratives about what came before. These insights are valuable regardless of whether Boltzmann brains actually exist in significant numbers. They're revealing deep truths about the nature of time, entropy, probability, and consciousness. Truths we wouldn't have discovered if we hadn't followed the mathematics wherever it led, even into uncomfortable territory. This is how science progresses, not by avoiding paradoxes, but by embracing them, by using them as tools to probe the boundaries of our understanding, by being willing to question even our most basic assumptions about reality. But the Boltzmann brain problem also reveals something profound about the human condition. We are creatures who need meaning, who need to believe that our lives matter, that our experiences are real, that our choices have consequences. The possibility that we might be spontaneous fluctuations, that our entire existence might be a cosmic accident lasting only moments, threatens this need for meaning at its deepest level. It suggests that the universe doesn't care about us, that we're not special, that everything we value might be built on an illusion. And yet, and this is the crucial insight, even if we are Boltzmann brains, even if our memories are false and our existence is temporary, that doesn't make our experiences any less real in the moment. Pain still hurts. Joy still uplifts. Love still matters. Beauty still moves us. The subjective quality of consciousness, what philosophers call qualia, is not diminished by being temporary or by arising from random fluctuations. A sunset is beautiful whether you're a human who evolved over billions of years or a Boltzmann brain that popped into existence 5 seconds ago. The beauty is in the experience itself, not in the causal history that led to it. This suggests a radical reframing of the entire problem. Instead of asking, "Am I a Boltzmann brain?" a question that might not have a definite answer, that might depend on arbitrary choices about reference frames and probability measures, we should ask, does it matter? If consciousness is what has value, if subjective experience is what's morally significant, then the distinction between quote, 83 observers and Boltzmann brains might be ethically irrelevant. Both are conscious, both have experiences, both deserve moral consideration. The universe might not distinguish between them, and perhaps we shouldn't either. The philosopher Derek Parfit spent his career exploring questions of personal identity and what matters for survival. He argued that what matters is not the continuation of some metaphysical self, some soul or essence that persists through time, but psychological continuity, the chain of memories and experiences that connect your present self to your future self. But Parfit went further. He suggested that even psychological continuity might not be what ultimately matters. What matters is simply that conscious experiences continue to exist, regardless of whether they're connected by memory or identity. In this view, you should care about future conscious experiences not because they'll be you, but because they'll be conscious, and consciousness has intrinsic value. If Parfit is right, then the Boltzmann brain problem loses much of its existential sting. Yes, you might be a Boltzmann brain. Yes, you might dissolve in moments. But other conscious experiences will continue to exist. Other observers, other minds, other moments of awareness. The universe will continue to generate consciousness, whether through evolution or through random fluctuations. And that's what matters. Not that you specifically continue to exist, but that consciousness itself persists. That the universe remains a place where subjective experience is possible, where there's something it's like to be something. This is not a comforting thought in the traditional sense. It doesn't promise you immortality or cosmic significance. It doesn't tell you that the universe cares about you personally, or that your individual existence has some grand purpose. But it offers something perhaps more valuable. A way to find meaning that doesn't depend on your individual survival, that doesn't require the universe to be designed for you, that doesn't collapse if you discover you're a Boltzmann brain. You're part of a larger process, a cosmic unfolding of consciousness and complexity. Your experiences contribute to the total sum of awareness in the universe, and that contribution has value, even if it's temporary, even if you're a random fluctuation, even if the universe will eventually return to a high-entropy state where no consciousness is possible. But let's return to what we don't know, because it's here that the future lies. We don't know how to build a theory of quantum gravity that successfully merges the smooth space-time of general relativity with the discrete, probabilistic nature of quantum mechanics. String theory offers one approach, with its vibrating strings in 10 or 11 dimensions. Loop quantum gravity offers another, with space-time itself made of discrete quantum loops. But neither theory has made testable predictions that would allow us to choose between them, and both face serious mathematical and conceptual challenges. We don't know what dark matter is, the invisible substance that makes up 85% of the matter in the universe, that holds galaxies together, that shapes the large-scale structure of the cosmos. We've detected its gravitational effects, but we've never directly observed a dark matter particle. It could be WIMPs, weakly interacting massive particles. It could be axions. It could be primordial black holes. It could be something we haven't even imagined yet. And we don't know what dark energy is, the mysterious force causing the universe's expansion to accelerate. It could be a cosmological constant, a property of empty space itself. It could be a dynamic field called quintessence. It could be a sign that general relativity breaks down on cosmic scales. We don't know. We don't know if the multiverse is real. Eternal inflation predicts that our universe is just one bubble in an infinite foam of universes, each with different properties, different laws of physics. The many worlds interpretation of quantum mechanics predicts that every quantum measurement splits the universe into multiple branches, each one equally real. String theory predicts a vast landscape of possible universes, perhaps 10 to the 500 different vacuum states, each one a potential universe with different physics. But we have no way to observe these other universes, no way to test whether they exist. The multiverse might be real, or it might be an untestable speculation, a mathematical possibility that has no physical reality. We don't know if the universe is a simulation. The philosopher Nick Bostrom has argued that if advanced civilizations can create detailed simulations of conscious beings, and if they choose to run many such simulations, then most conscious beings would be simulated rather than real. This is structurally similar to the Boltzmann brain argument. Simulated beings vastly outnumber real beings, so you're probably simulated. But we have no way to test this hypothesis. No way to detect the, quote, 86 or, quote, 87 that would reveal we're in a simulation. The simulation hypothesis might be true, or it might be unfalsifiable metaphysics dressed up as science. We don't know if consciousness can be uploaded, if your mind could be transferred to a computer or a new biological body. This depends on whether consciousness is substrate independent, whether it's the pattern that matters rather than the physical medium. If consciousness is just information processing, then in principle, it should be uploadable. But if consciousness requires something specific about biological neurons, quantum effects, microtubules, some yet unknown property, then uploading might be impossible. And even if it's possible, there's a philosophical question. Would the uploaded version be you, or would it be a copy while the original you dies? This is another version of the identity problem that the Boltzmann brain scenario raises. We don't know if there are limits to knowledge, questions that are, in principle, unanswerable, even with unlimited time and resources. Gödel's incompleteness theorems show that mathematics contains true statements that can't be proven within any consistent formal system. Does physics have similar limits? Are there questions about the universe that are true but unprovable? Are there aspects of reality that are forever beyond our understanding, not because we're not smart enough, but because the questions themselves are ill-formed, or because the answers require concepts we're incapable of grasping? The Boltzmann brain problem might be one of these fundamentally unanswerable questions. It might be that there's no objective fact about whether you're a Boltzmann brain, that the question depends on choices about reference frames and probability measures that have no unique, correct answer. Or it might be that the question is meaningful, but we'll never have enough evidence to answer it with certainty. Or it might be that future physics will dissolve the problem entirely, showing that our current formulation is based on false assumptions about time, entropy, or consciousness. But here's what we do know. We know that we're conscious. We know that we have experiences. We know that we can think, reason, feel, wonder. We know that we can do science, that we can build theories and test them against observations, that we can gradually expand our understanding of the universe. We know that we're part of something larger than ourselves, that we're connected to other conscious beings through language and culture and shared experience. We know that we can create meaning, that we can find beauty and purpose and value in a universe that might be indifferent to our existence. And we know that the act of questioning itself, the willingness to confront uncomfortable possibilities, to follow arguments wherever they lead, to admit ignorance rather than pretend to certainty, is one of the most distinctively human activities. The Boltzmann brain problem is not threatening your existence. It's inviting you to think more deeply about what existence means, about what makes you real, about what gives your life value. And by accepting that invitation, by engaging with these questions seriously and honestly, you're already demonstrating that you're more than just a random fluctuation. You're a participant in the universe's ongoing attempt to understand itself. The physicist John Wheeler spent his final years thinking about what he called the, quote, 88. The idea that observers don't just measure reality, but help create it through their observations. In quantum mechanics, the state of a system is undefined until it's measured. Wheeler took this seriously. The universe doesn't have definite properties until conscious observers measure those properties. In a sense, observers bring the universe into existence through their observations. This is not solipsism. It's not saying that you create reality through your thoughts. It's saying that reality is a participatory phenomenon, co-created by the physical universe and the conscious observers within it. If Wheeler is right, then the Boltzmann brain problem takes on a new dimension. You're not discovering whether you're a Boltzmann brain. You're deciding what kind of observer you are, what kind of reality you participate in creating. Your choice to trust your memories, to engage with the world, to act as if you're real. That choice is not just a pragmatic strategy, it's a creative act. You're not just observing the universe, you're helping to define what the universe is through your observations and your choices. This brings us back to where we started, to that moment 5 seconds ago when you might have popped into existence. Remember that opening hook? The possibility that you spontaneously assembled from quantum fluctuations, that your entire history is a false memory, that you'll dissolve back into chaos in moments. We've traveled through thermodynamics and cosmology, through quantum mechanics and consciousness, through mathematics and metaphysics. And now, we return to that original question with new understanding. Are you a Boltzmann brain? The honest answer is, you can't know for certain. The mathematics suggests it's possible. The cosmology suggests it might even be probable under certain assumptions. But the very fact that you can understand this argument, that you can feel troubled by it, that you can choose how to respond to it, that proves you're more than just a random fluctuation. You're a participant in reality, not just a passive observer. You're part of the universe's ongoing conversation with itself. And here's the final insight, the one that makes all the uncertainty bearable. It doesn't matter whether you're a Boltzmann brain. What matters is what you do with your consciousness, however it arose, however long it lasts. What matters is that you're here, now, aware, capable of wonder and curiosity and love. What matters is that you can read these words, think about these ideas, feel the weight of these questions. That's real. That's enough. The universe is vast and strange and indifferent. It doesn't care whether you exist. It doesn't care whether you're a Boltzmann brain or an evolved human. It doesn't care whether your memories are real or false. But you care. You wonder. You seek meaning. And in the universe that might be nothing but random fluctuations in an eternal void, that caring, that wondering, that seeking, that's the most remarkable thing of all. That's what makes you real, regardless of what the mathematics says. That's what makes your existence matter, regardless of how improbable it is. We are the universe becoming conscious of itself. We are matter and energy arranged in patterns complex enough to contemplate their own existence. We are the question and the questioner, the observer and the observed. We are, in Carl Sagan's beautiful phrase, quote, 89. And whether we're evolved beings or spontaneous fluctuations, whether our memories are real or false, whether we'll exist tomorrow or dissolve in moments, none of that changes the fundamental miracle of consciousness, the sheer improbability and beauty of awareness itself. So embrace the uncertainty. Live with the doubt. Accept that you might never know for certain whether you're a Boltzmann brain. And then, get on with the business of being human, of loving and learning and creating and contributing to the collective project of making sense of this strange, beautiful, terrifying universe we find ourselves in. That's not a solution to the Boltzmann brain problem. It's something better, a way to live that makes the problem irrelevant. You are here. You are now. You are conscious. And that's all you need to know. The rest is just physics.